Hello, everyone, and welcome to another Pivotal Data Science webinar, How to Make Cars Smarter, a Step Towards Self-Driving Cars. I'm Jeff Kelly. I'm a member of the Pivotal Data Product Marketing team, and I'm joined by our two speakers. Esther Vassiette is a data scientist at Pivotal, where she has engaged in data science labs with customers from multiple industry sectors. She received a master's in electrical engineering from the University of Colorado at Boulder and collaborated with the HCI group within the computer science department to bring data science models to smartphones. She also has experience in image processing and computer vision in collaboration with the Computer Vision Center in Barcelona. Our second speaker is Kaushik Das. He's a senior principal data scientist with Pivotal. He leads a team of highly accomplished data scientists working in numerous sectors, including energy, autos, telecommunications, retail, and digital media. Kaushik has an engineering background focused on solving mathematical problems requiring large data sets. Kaushik studied engineering at the Institute of Technology at the Banaras Hindu University and the University of California at Berkeley. With that, let me turn things over to Esther and Kaushik for today's presentation. Take it away.
Thanks, Jeff. So today, we are going to talk about smarter cars, and so we start by defining that term. What do we mean by smarter cars? And then we go into the details of how to apply data science to actually build smarter cars, and we'll discuss a couple of examples, one on predictive maintenance and another focused on the driver, on understanding driver behavior patterns. And then we go to an exciting part where we actually show you some examples of the code that we have used to build and run these models. And then we conclude with next steps, your questions, and our answers to your questions. So let's start by some definitions. So many advantages. And the idea is that when any of us humans want to go somewhere, we call a car and we get into the car, we sit and relax, and then we are there. So what this does is that it removes a lot of stress to begin with, right? We don't have to drive in traffic. We don't have to worry about maintaining the car. The car takes care of itself. We essentially are sitting there. We can take a nap. We can lower the backs of our seats, like at a first class of a plane, and actually read something or talk to our friends. And one of the big other impacts is that there are actually fewer accidents and injuries. But there is a but, and the but is that there is still some issues that need to be resolved. And I'll go a little bit deeper into that, right? Because there are a couple of things. There are technical things and legal things. The legal things, for instance, is that the newest California law about autonomous cars says that you need to have a driver ready to take over in case of an emergency. So you can't actually sit and relax right now, as the law stands right now. So when we think of autonomous cars, we're thinking of trying to get from today's world of manually driven cars to autonomous cars. But what we are suggesting here today is that the path is really through smart augmented cars before we get to autonomous vehicles. Now, I don't know if you guys have seen that I think today or yesterday, Elon Musk tweeted about actually having the hardware ready to basically get Tesla drive autonomously. But if you look carefully, there are still some issues before we get to that point where the true vision of autonomous cars is realized. One of the things you will see is that, a driver has to still be there and sit there with his hands almost on the wheel, basically ready to take over. So, and then, there are the acceptance issues, right? And in some ways, the legal part is also because of the acceptance issues. So for instance, May 7th this year, we had one driver of a Tesla on autonomous mode actually die because the sensors of the vehicle were unable to see the truck which was in front of the vehicle because it had a reflective surface and it couldn't distinguish it against the bright sky. So there are still a lot of issues with autonomous vehicles, and we are able to get around them if we start making smart cars, and then that naturally leads us to autonomous cars. So when we talk about smart or augmented cars, that's not a term that we came up with. So an augmented system is defined as a situation in which humans and computers combine to create effective and efficient outcomes. And the result is that you get reduced stress and fewer accidents. So you're still moving in the direction of reducing stress and reducing accidents. There are many fewer regulatory or legal barriers because augmented vehicles have already started appearing on the scene. For instance, a lot of vehicles now will actually have warnings if you're changing a lane and if there's another car near you, or they would even apply the brake if you're about to crash. And they're, of course, much easier to implement. So let's go into talking about how you actually build that and what do we mean when we say a smart augmented system. So a smart augmented system essentially uses a biological organism as the metaphor. And what we mean by that is that we need a sensory system, we need a motor system, and we need a nervous system with a brain, right? So the sensory and motor systems, basically the hardware and the total systems for those already exist today. The interesting thing is building the brain. And that's what we're going to talk about a little bit today. And the way we build the brain is using a big data platform while implementing a data science model within that platform. And how do we do that? So we have a certain methodology for implementing data science, which we call the eightfold path of data science. And what it incorporates is 4 simple phases, which we have borrowed and evolved from the pre-existing CRISP-DM methodology for analytics. And those 4 phases are basically formulating the use case and then going into the data step, where we actually look at all the data that is available and we build feature sets, which are essentially the input variables that go into our model in the 3rd step. We build a model based on all the data that we have, which makes our model more accurate rather than taking a sample of the data. And then we build the application which will apply that model in a real life situation. And there are 4 differentiating factors that we need to keep in mind. Firstly, we need to select the right technology. Secondly, we need to have an agile iterative approach during this project because we'll have to modify and learn as we go along. And then we also need to be creative at every phase of the project because there is always the chance of doing something new. And in the end, we have to build a narrative because remember, one of the barriers we have in doing such projects is the acceptance factor. And the human beings who are actually going to use the car need to have some degree of control and understanding over what's going on. So when I mention technology, what do I mean? So this is, actually a great thing that we have a lot of tools available now. So the projects that we do, being the data science team within Pivotal, we actually use of the Pivotal software, and we actually also inspire the Pivotal software so that it kind of does exactly the things we are talking about. So on top, you will see the platform elements, right? There is the massively parallel database Pivotal Greenplum. There is the Hadoop system, Pivotal HDB. There is Spring Cloud Data Flow for orchestration of the different elements. And then, there are elements like Apache Spark and Pivotal HDB. So based on this platform, we have, and these are all based on open source standards, which gives us a lot of choice in terms of the modeling tools, as well as visualization tools, which are essential for data scientists. I will quickly mention one of the tools that we use a lot because that is something we have developed in-house at Pivotal. And actually, this is something that's now incubating on Apache. So it's an open source project. And that's a set of machine learning libraries which have been parallelized so that they can work on big data. So normally, if you're using, say, the platform like Greenplum or Hawk, you can use any sort of library, whether it's a Python library or R library. But those really are parallelized only in cases where your algorithm is data parallel. So basically, when you're running a bunch of small functions. But when you have to invert a big matrix, as you often have to do when you do a true machine learning algorithm, and we will go a little bit deeper into that in the example, then you need to explicitly parallelize that function. And that's what MADlib does. And this is a snapshot of some of the things that are available on MADlib. And this is open source. I encourage you to go and kind of play with it. But this gives us a kind of ready-made parallelized algorithms so that we don't have to spend a lot of time in doing that parallelization. And then comes to the phase one, once we have an idea about a familiarity with the technology and the tools, we really need to start with the specific use case. And when you think of how to make a car smarter, there are three sets of use cases really. The first is the car itself. Is the car functioning as it should? Do any of the parts need servicing or replacement? And there is that whole recall issue that manufacturers have to face when they introduce new parts. How are the new parts functioning? Are they functioning as we thought they would based on the in-house tests? Because remember, the tests that manufacturers do on parts and cars are on test tracks and simulated environments. And then when you release it and, thousands of drivers are using it in conditions which were not entirely foreseen by you, they might actually function differently. And now we have the ability, because cars are connected, to get that data from real life situations and answer these questions. The second set of use cases is focused on the driver. And there is a paradigm here called advanced driver assistance systems. And these already exist. I gave some examples before of like warning you when you're taking a turn and things like that. So this is really about understanding the driving patterns that different drivers have, typical routes they take, and then customizing to the individual driver so that you can respond to that individual driver in the appropriate manner. And then there is the greater surrounding of the cars, right, which is the traffic situation and the roads. So how do we improve congestion forecasting? How do we optimize routes better? How do we improve traffic management, like the algorithms that control the traffic lights? And in a longer time frame, how can we actually improve city planning itself so that we are using very granular driving and traffic information which is available today rather than sample studies. So it's a really exciting set of use cases that we have. And I really want to emphasize that when we talk about smarter cars and augmented systems, we're not just talking about having a car drive by itself. We're talking about the whole picture which affects everything that affects the driver and the user of these cars. One of the other things I want to mention is the data part. So that's really one of the big things that have changed in the recent past, that there is a lot more data available. So for instance, the car itself, there is data that we get from the manufacturing process. There is data that we get based on the parts. There is data that comes from the connecting the car itself. So cars today have a lot of microprocessors which basically register diagnostic trouble codes or DTCs, and they can be accessed by a standardized port which exists in every car, which is called the OBD2 port. So when you take your car to the mechanic, that's the first thing they do today, is that they will connect their diagnostic computer to the OBD2 port and download that data. But what we can do is then actually stream it on a regular basis from a connected car. So you don't have to wait till you get to the mechanic. And we'll talk about one specific example there. Then there is data from the dealership, sales and leasing, service data. And then there is consumer data, which focuses on the driver and the surroundings. So for instance, demographics, there is CRM data, surveys, there is driving behavior data, details about the initial sales. And finally, there is data from the external situations which affect driving, that is traffic, weather, the economy, right? I mean, how much crowds do you expect and how much congestion do you expect can be affected by that? Special events. And then data from, there are a lot of external sources nowadays like Ganip and Factual who can give a lot of data which would be useful for us. So this kind of, sets the stage at a high level for the very exciting situation where we're in, where we have cars which are ready to be smarter, where we have the tools ready to make them smarter, as well as the data to build the digital brain. Now let me go deeper and so that we can figure out how actually we do this. So the first example we have is a smarter car, and I'll hand over to my colleague Esther to talk about that.
Yeah, thank you, Kaushik. So I'll talk about how to make smarter cars from a preventive maintenance standpoint. So we partner with a major automobile company to make better use of onboard diagnostic systems. These systems are responsible for signaling a series of diagnostic trouble codes or DDC codes. And so here, for instance, you're seeing one of those codes like P0302, which gives information about the type of problem if there was a problem in the car. So for instance, this one refers to misfire detected in the second cylinder of the car. And even though this seems like a very specific code, going from this particular code to an actual repair done by the mechanic, it's not really clear. So there's actually many of these DDC codes that are not really showing any symptoms of a particular problem. And so it has been hard to come up with a rule-based approach to find the right repair. And so instead, a machine learning approach that learns from a lot of historical data is a better way to learn this relationship between a series of DDC codes that happen during a certain period of time and a particular repair that it's an unscheduled kind of repair in the future. So on the next slide, we can see that in order to solve this problem, we need data. And in this case, the data come from two very different data sources. And these are data sources that were previously disassociated, so they have never been used together. So the first data source is the vehicle data, right? So we have a lot of, sorry, can you go back to the... the first data source is data about the vehicle, such as the DDC codes and other type of sensors, such as the speed, the acceleration, the temperature, and so on. But on the other hand, we had data from all of the dealerships, right? So dealerships are the ones where they repair the cars. So we have data about the car coming in, going out from the repair, which kind of repair was performed, was it in warranty or were any parts replaced, and so on. So those are the two different data sources. And so on the next slide, we can see how we can use these two different data sources to set up the problem in a supervised framework like this. So from one side, we have all the DDC codes that happen at different time points in times, and you can see those in this blue line. So these DDC codes could happen in the same day, could happen a lot of them, or they can be repeated in time. And then we also, from the other data source, we have those red lines, which correspond to the time where the owner of this vehicle brought a car to a dealership to perform some sort of repair. So given that we have these two different data sources, the question that we wanted to solve was, given that we have seen all these DDC codes happening previous to a repair, could have we predicted that this car needed, that particular kind of repair? So it could be a transmission kind of repair, but also note that at a given point, a car sometimes needs a repair in different types, such as a transmission and an engine. And so that's the kind of problem we're trying to solve using machine learning. And so in the next slide, I show how we actually went and solved it. We decided to follow a hierarchical classification framework where in the first stage, we aim to predict the type of repair. So is it a wheels kind of problem, or is it an engine kind of problem? And so we're just focusing on the high level, but not the actual repair code, because there's a lot of different kinds of repairs. So in the first stage, we're just focusing on the high level, and we're doing this with a one versus rest logistic regression models. And we use the one versus rest approach because as I mentioned earlier, there could be one problem, but there could also be more than one. So it's a multi-class and also multi-label classification problem. And then given that our models on the first stage, if they signal as in you need a particular kind of repair, then there's a second stage where we would score it on a random forest. And these second stage models, these are specialized models, because on the second stage, we have only trained these models using training data from cars that actually needed that particular repair. So for instance, if on the first stage, given a set of vehicle features, and these features are the DDC codes that I talk about, but also many other features. So given those features, if the first model thinks there is an engine kind of problem in the car, then we would feed we would feed these features into the second stage to a random forest that has only been trained on engine-related issues. And so in the next slide, we can see how by doing this, so by doing this, potentially your car could be repaired before you have a problem. And this is especially true for, we found this to be actually true for software-related repairs where we had the best accuracy, but also being able to predict some of these failures in advance could potentially prevent more serious failures in the future. All right, so that was a first use case. I'm also going to be talking about the second use case that I'm actually really excited to show, because we get to show some of the work that we have done with our partner, Denso. So Denso is the second largest auto part manufacturer in Japan and the fourth in the world. At Denso, their R&D team has been working towards understanding driving behavior in an unsupervised manner using machine learning techniques. This approach is very interesting, actually, because they adapt techniques that are very common in natural language processing, but they use it towards capturing driving patterns that will help them create a smarter driving response. So I actually invite the audience to refer to the paper below for all the algorithm details, but basically I'm going to give a very, very high level of overview of the algorithm. But basically, Denso collected a lot of data from their cars and took a lot of trips on those cars around LA. And so from this data that they collected, the first step is to divide these trips into segments that are meaningful. So by dividing the trip into meaningful partitions that they call scenes, they get to explain those scenes into a second stage of driving topics. So they use what so the segmentation is done with a technique called hidden Markov Model that I'll be showing some code about how we went on to scoring and getting those segmentations of the scenes. And then after we have those scenes, we derive driving topics using an algorithm called Latent Dirichlet Allocation, or LDA, that is available on MATLAB. So as Denso was facing scalability issues of this algorithm, we helped them translate this research, explained in more detail in this paper. We helped them translate the research into Greenplum to enable their R&D team to speed up future research. And because we were using Greenplum, we were able to take advantage of the parallelism of the task by using PL/Python and also using the LDA implementation in MATLAB. So on the next slide, we can see a typical MPP, massively parallel processing database structure. So in an MPP database like Greenplum, the data is distributed across segments where each segment has been harnessed with Python, R, or any other library that we need. And so in our case, as I mentioned earlier, we're using a hidden Markov model, so we're going to use an open source hidden Markov model implementation using the HMM-learn library. And so this library has been installed in each of the segments so that we can actually perform trip segmentation into scenes in parallel, given that the data from each trip has been distributed across segments. So there is no need for the data to move across segments, and this can run really fast. And so this is something also that I'll be showing you very shortly. But before I do that, in the next slide, I just want to quickly give an overview of the latent Dirichlet allocation algorithm. And so as I mentioned earlier, this is an algorithm that it's really commonly used in natural language processing. So imagine you have a set of documents, a lot of documents, and then you can explain these documents using a back of words approach, which basically means given your vocabulary, you're going to count the number of times that a word appears in that document. And so each document you represent it with this back of words vector. And then LDA, what's interesting about LDA is that it's able to get all these documents explained with the back of words and is able to infer a number of topics. So these topics are basically a collection of words where a given topic has some words that are most prominent. And so for instance, here in this example, we can see that one of the topics tends to talk about genomes and DNA. And so it has learned from all the documents, across all the documents, that, some of those seem to talk about this genome stuff. So that's one topic. And then there's other topics such as computer-related stuff. So this algorithm, we can also use it to understand driver behavior, and then so did that, where a document, in our case, is one of those scenes, and a word is a quantized sensor value. So a value that you get from a quantized sensor value from the accelerometer or the brake or the speed and so on. And so having given this overview of the algorithm, I think I'm ready to show some code. And so bear with me while I change the mode into screen sharing so that I can show some code. And so hopefully right now your screen has changed and you're able to see a Jupyter Notebook. So for those not familiar with a Jupyter Notebook, is basically a web browser. It's a web browser where you can hit some code, but also it's really good for data scientists because we can run some code and also see visualizations and have some explanations. So it's a very nice way to have a full data science pipeline in here. But basically, the first step would be to connect into the database, and so we are able to connect to the database through a library called PsychoPG2. It's not really important, the details of the connection, and so hopefully I'm able to connect. So this is, of course, live, and right now I'm not sure I'm able to connect. It's taking a little bit longer than I expected. But in any case, I'll keep showing the code. So once you connect to the database, you're able to see that I don't think it's connecting. So I'm gonna stop sharing real quick. I'm gonna make sure my connection works, and I'll start sharing the screen real soon.
Okay, well, while we're waiting, we do have a few questions, and perhaps some of these might be answered throughout the presentation, but while we're waiting, why don't we take this time to talk a little bit about some of the questions. One question is more about the kind of the industry and being ready for these types of smarter car applications. Either Kaushik or Esther, just curious, what is your opinion in terms of where the market is from a car manufacturer perspective in terms of outfitting their cars with enough data creating sensors that you're actually going to get enough information and enough data to run your models and actually do something useful and actually put some of these use cases into practice? Are we far along there? Are most car companies kind of moving in that direction? What are your thoughts?
So we are actually very close, Jeff. So all the major manufacturers already have programs, small or big, which are actually, they have a connected car fleet already, and they are actually streaming some data. So the thing, though, is that it's more about the taking these to the drivers and customers. And so what we are seeing is that the different programs are in place, and the technology is not is ready, but it's a question of doing these programs, which involves involving marketing and sales and actually putting it in front of customers. And of course, once these programs start operating, we will also see new challenges, right, as we scale it up. and that will lead to changes on the technology side as well. So for instance, one big question is about edge analytics, right? How much analytics do you want to do in the car itself before you send the data on to the central hub? And that again depends on the use case. So these are kind of very interesting questions we're dealing with. But I think that, in the next year, we will actually, all of us will be able to see these programs from most of the major manufacturers.
Great. And so, I mean, as we're looking at from a timeline perspective, just put you on the spot a little bit. I mean, we hear things about, we're going to see autonomous cars by, I don't know, 2025. Some of the car companies are saying, or maybe even earlier. What is your opinion on when you think, not necessarily autonomous cars, but some of these smarter cars are more kind of mainstream? Are we within a couple of years where the majority of us are going to be driving these types of cars, or is it a little further out?
So for the smarter cars, I think definitely a 2-year time frame is very realistic. For a fully autonomous car, it will take more time, because the problem is that the technology today will work for a certain set of conditions and not all conditions, right? So that's why you still need an augmented system. So the smarter cars will definitely be mainstream in a 2-year time frame. I should not say definitely, of course, because prediction is always difficult. But that's our prediction.
Got it. Okay, great. Esther, I'm seeing your screen again. Are things connecting?
So
okay, great.
I'm
I'll let
good.
you take it back.
Great, thank you. So sorry about that little technical difficulty, but yeah, so I'm able to now show some of the actual real data from some of these trips that Denso took with their cars. So we started our the engagement with two tables in the database. One table contains all the raw data, which has been distributed by trip. And so this data looks something like this, where you have a trip, you have a timestamp, every 100 milliseconds has been updated, and then we have the GPS coordinates, and we have the acceleration, the brake, the steering angle, and the speed. Denso also has some more sensors, but we are only showing this because those are the ones that we mostly use for the algorithm at this point. But this is how the data looks like. And then we also have a model in the database that has as a byte array that it's a model that Denso had already trained. It's the hidden Markov model that they already had work on. And that doesn't mean, because you have trained this model in Python, that doesn't mean you cannot use it anymore once you bring it into Greenplum. The thing is that you can easily load that model in Greenplum and use it to score. And so that's the next thing that I'm going to show. Probably before I do that, though, I also want to show how we can maybe look at some of this data in terms of some time plots, time series plotting. So this is the acceleration opening for one trip, just to show how it looks like. Then the brake pressure for a trip as well, the same trip. And so, of course, the data is really big, but if you only load into a data frame in Python one trip at a time, that's how I'm able to show these plots. So that's the next plot is for the vehicle speed. So you can see how this is usual time series data. And so, so now I'm going to show the HMM inference using a model that has been loaded from the database. And so we do this using procedural languages derived from Postgres, and in this case, where you're going to use PL Python, because when you're doing research, maybe you have in the past used Python code to do your modeling, and you could even copy pretty much the same code that you had done and bring it into Greenplum very easily with PL Python. And so basically, you just need to define a function by saying what's the input of your function, what are the input types. So for instance, we're going to input a trip ID, And also look at here how we're inputting the byte array, which is the HMM model, and some normalization parameters model into an byte array as well. And then everything that is inside the $$ sign, it's completely normal, completely usual Python code. So I'm not going to go too much into all of the code because there is a lot of code, but I just want the audience to look at how you would import libraries such as NumPy or Pickle to load that model, or this library that I mentioned earlier, the HMM learn. So we can import these libraries at each segment and have this Python code run across multiple nodes, and so we can process this in parallel. And so by using the Pickle library, we can just load that model and use it. And so that's the Python PL Python function, which ends with a $ sign and language PL Python. So that's how you know it's a Python function. And then I'm going to show next how you actually call that function. And in order to do that, I just want to very quickly show some inner queries where the first thing that we do is we get all those sensor data that we care about, which is the accelerometer opening, the brake pressure, the steering angle, and the vehicle speed. We join that into an array. And then the next thing is that we're going to group by a trip ID. And what this is doing, the group by trip ID, is basically going to aggregate all of our data by trip ID. And you see that how we are aggregating using this array ag array. We're aggregating each array independent row-wise into a massive array that we call features linear matrix. And then that inside the Python code, we just make a normal matrix. But basically, because of this group by trip ID, we have all of our data in one row. And then the last thing that I want to show is how this HMM inference, this is the Python function that you call. And it's very easy to call. You just do select HMM inference. And here you have your parameters. Some of these parameters are the model parameters that were loaded from a byte array. And because of the group by ID, trip ID, that's how we can run that in parallel. And so actually we were able to do HMM inference in 7 minutes, 45 seconds on 11.3 million rows of data. So that was pretty fast. That was definitely faster than what Denso had done earlier. And so the result of that function is basically the same data, but now for each timestamp, we have the scene ID. And so as I mentioned, the first step of the algorithm is to divide a trip into scenes. And so we have successfully, pretty quickly in parallel, achieved that. So the next thing that I want to show is just maybe some map of this data. So Denso collected all this data in LA. And so this is some of using the GPS coordinates, we can see in a different color the start of each in the different scene. So a different point in this map represents a different scene. And so this is only one trip. In this case, I think it's trip 51, but I can also show a different trip. And so this is a different trip. And we can see each point is the start of a new scene. And so the next step was for each scene, just quantize those features. Quantization is also done in parallel with a PL Python function that is called Quantize. I'm not, just given the time, I'm not going to show the Python function, but same idea, because we're doing because we're doing this by row, and the data doesn't need to talk to each other. We can just spin up a bunch of Python instances across multiple nodes. And the result of that quantization is basically for each trip ID at each timestamp, we just have a quantized vector, which is basically per each feature, and we have each features, what's the vinerize, the vin that particular sensor value falls into. And so the next thing would be to prepare the back of words vector that I mentioned earlier that we need for LDA. Back of words vector basically looks something like this, where for each strip and each scene, we have all these features, and then we just need to count them. So that's basically a back of words. Each feature, how many times does it appear in a particular scene? And so that would be the input of our LDA, the LDA MATLAB implementation. Only MATLAB implementation basically needs a table where you have a document ID, a word ID, and count. So basically this is the same table, only I have just changed the feature names as a word ID, but otherwise it's the same thing. And this is one of my favorite parts because now it's when we get to do LDA inference. And I just want to show how easy it is to train an LDA algorithm using MATLAB. It's basically like a very short code. It's basically you do select matlab.lda train, and you put your input parameters, which is the input table, where do you want your model to be saved, where do you want your output table to be, the vocabulary size, and some other parameters, such as the number of topics. So we use 10 topics to show, but in the paper, actually, Denso uses 25 topics. And so after you have trained the LDA algorithm across documents, and again, documents here are scenes, we can see the results where we see for each scene what's the word and the topic assignment. So I'm running kind of out of time, so I just wanted to show that it's really simple to use MATLAB. I would invite you to use it. And then the last thing that I want to show is that I hopefully would give a better implementation of what this topics means is that LDA has gotten all these trips, and in an unsupervised manner, and by unsupervised I mean there hasn't been any human telling the machine what these things mean, but LDA is able to extract significant topics. So I want to show you some of these topics that we were able to find. For instance, one of the topics contain words such as driving near 84 kilometers per hour or driving near 77 kilometers per hour. Also, we have words such as constant gas, not changing directions, continuous brake pressure. So this topic basically means normal highway driving, where you're just, like there is no acceleration or you're just driving straight at that particular velocity. So that's one topic. And then we have another topic where it's clearly about turning left or turning right. And because we're turning right or turning left, we're also going very slow. So we're going around 7 kilometers per hour or 14 kilometers per hour. And so it's very interesting to me how this algorithm is able to find these topics. And then just to show another topic, there is this topic number 9 is about braking. So you see how all of these words are brake, 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 or driving extremely slow, or almost even stopping. So again, the machine has been able to learn these topics from the algorithm, so I think it's very interesting. And I think I'm going to stop it here. Hopefully that was interesting, and I'm going to leave it again to Kaushik.
Thanks, Esther. That was really interesting. So, all the bag of words, all the word clouds that Esther showed at the end, they actually all refer to certain specific locations. So it gives us a lot of information about driver behavior at certain locations. So there is a driver element as well as the location element there, which is quite interesting. So, essentially, I want to kind of end by showing quickly that what would be the architecture when you operationalize it, right? Because I mentioned the platform and tools. So in this case, what Esther showed, you would operationalize it by taking in the data feeds, which is the sensory part of the smart system. And then when you build a nervous system, we are using Spring Cloud Data Flow, which is an element of the Pivotal Cloud Foundry network for orchestration. And then getting the data into Greenplum, where all the processing and modeling takes place, where we are using tools like PL Python and Madlib. And then we could actually, with the part that we didn't show, is that surface them using apps, again within Pivotal Cloud Foundry, running within Pivotal Cloud Foundry, and that would lead to a feedback loop, which would lead to continuous model improvement. Basically, we'll be able to improve your driving experience by preparing your car for the exact conditions that you're about to encounter. And in general, it's easy to make cars smarter. And to the point of one of the questions that Jeff was asking, that how long will it take? So all the elements are there, right? And there are, of course, it's difficult to predict precisely, but I'm pretty sure it is going to happen very quickly. And it's already happening in small doses. So I would, at this point, like to conclude this presentation by thanking two sets of people. One is our colleagues. So Esther and I are presenting a lot of knowledge based on projects which has been done by amazing data science team and data engineering team within Pivotal. And I would specifically like to call out Raghunathan Radhakrishnan, whose deep knowledge has been instrumental in making a lot of this happen, and as well as our partners. We were happy to share today's presentation with by mentioning Denso, but we've actually worked with a lot of manufacturers in Detroit, as well as in Germany, Japan, and Korea. With that, I will hand over to Jeff for more Q&A.
Great. Well, thank you, Kaushik and Esther, for a great presentation. Hope the audience enjoyed it. We do have a couple minutes left for some questions. One question we have is wondering if you could, either of you could kind of expand a little bit on the concept of analytics and where it actually is being processed, whether it's in some kind of cloud environment or whether it's actually out on the edge on the car itself, and talk about the different factors that go into determining where you're actually going to put the compute and actually do some of the analytics. I'm assuming, for some of those use cases where you're actually trying to impact the operations of the car in real time, that analytics probably has to take place in the car versus some preventative maintenance. You might be able to do that in the cloud because it's not as necessarily time sensitive. But anyway, I'm wondering if you could expand on your thoughts on that a little bit more.
Yeah, so that's really a very good question. So whenever you do data science in the Internet of Things, we are talking about an extended system here. So it is not just that the car is an independent unit. It's part of it's connected, right? So it's part of a big network, which is the smart system. So what we are doing is that we are getting the data from the cars to build a batch model in a centralized location. That way we can use the information from our entire network of cars to learn the patterns. And then when it comes to execution, that happens at the car, and that uses the the model coefficients and essentially the output of the model which has happened in a central location. So, again, if you think of how a human system works, our human body works, right? Our brain is doing a lot of processing, but there is a lot of reflex action that's going on at the level of the different organs like fingers and toes, which doesn't necessarily go to the brain, but which benefits from the learning that the brain has done. So again, and how much of it is done in the centralized unit and how much of it is done in the edge depends on the specific use case.
Great. I think that was a really good analogy as well. Another question about data sources. So we talked about data sources coming from the car itself, data sources from the manufacturer. What about data sources like, or I should say, maybe not data sources, but data points related to other things, maybe outside the car, like weather, traffic, other kind of conditions. How do those play a role in some of these use cases?
Yeah, so actually, we did a lot of work. We have done a lot of work on predicting traffic and congestion. So in the reference, you will see some of the blog posts which will go into more detail. But essentially, there are two ways that we are seeing a lot of traffic data. One is from within the car, right? Whether it's the connected car sensors or the app. Then the other is the traffic system itself. So increasingly, there are pilot programs in many cities, and some cities are more advanced than others. For instance, San Jose, actually, you actually have the data from most of the traffic lights. They're actually instrumented. So these two data sets are giving us a lot of information about patterns of traffic, at a very granular level, right? At the level of minutes and even seconds, so that you can see that what are the normal patterns that exist and what is the variability across those patterns, which helps us smoothen out traffic a lot.
Okay, great. Well, thank you guys so much for this presentation. I think it was really helpful, and I learned a lot. I know that much. I hope you, the audience, also enjoyed this presentation. You'll be able to find these slides online shortly, as well as the recording of the webinar itself at pivotal.io. So please check that out. Kaushik, if you could just move to the resources slide. I just want to point out a few other resources that our audience might be interested in. There we go. So you can check out, yep, I've got it. You can check out blog posts from our data science team over at the Pivotal blog. You can see the link there. If you're interested in a Pivotal Data Science Analytics Roadmap engagement with us, please feel free to reach out at pivotal.io/contact. Of course, this is one in a series of webinars around data science here at Pivotal. We'll have another. The next webinar will be sometime in Q1, exact date to be determined. We'll be covering how data science can help with fraud detection and cybersecurity. So please stay tuned for that. Check out our resources page, our webinar page for more information. And finally, if you want to get your hands on some of this technology, there's some links there for downloading sandbox versions of Pivotal HDB, Greenplum, as well as you can go ahead and download Apache Madlib, that machine learning library for distributed systems. So thanks again, everybody, for joining us. Really appreciate it. Thanks to our presenters, Kaushik and Esther. Did a great job today. We'll look forward to seeing you next time.
Thank you.
Thank you.